Okay, thank you. So I will try to briefly update. So now we are moving to the surface and the land surface modeling. So what have we done and what are we planning to do in CAMS 252A? So this involves a lot of colleagues and including also especially the people that are developing CTSL at ECMWF. So the main objective of this Copernicus project is two parts. First is to work on the wetland methane emission model and to improve it, to improve this model within CTSL IFS. And the second part is to work on the carbon cycle and the photosynthesis through the computations of for the inclusions of a solar-induced fluorescence model within CTSL in order to further later assimilate solar-induced fluorescence data from space. So I'll start with the wetland flux modeling. The context is a bit, so you all know that there is a large variability in the atmosphere of wetland concentration. And here, this is the NOAA mean atmospheric growth rate. And we see on the left that the last 2 years were with the highest growth rate, despite the lockdown due to the pandemics. 2020 and 21 have the highest growth rate in methane. So one of the potential candidates to explain these large variations, not the only one, but it's from the natural fluxes, the wetland extent, which are the dominant part of the natural fluxes. So basically, a lot of studies are ongoing to relate the changes in natural wetland, especially for 2020, due to an increase of potential fluxes in the north to explain part of the increase of the growth rates in 2020. So in this context, what we have done, so this is the people that are working in these aspects of the project. What we have done in the previous phase, in CAMS 41, we have implemented a statistical model in CTSL. Basically, it's a simple model where you have A, the wetland extent, R, the carbon available, and the Q10 function of the temperature, and of course, an overall global scaling factors. So we had that model, and we want to improve because it's still not yet capturing all the variability that we would like to have in IFS. So the current work, the focus that we are doing now, and sorry, the project has only started from 6 months really, so it's not a lot of results, is to replace the monthly climatology of the wetland extent that is currently in the IFS by something more dynamics. And we have two satellite-derived products, the WAD2M and the GIMS product. The WAD2M is produced by Ben Poulter, and it's the official standard product used for the global methane budget of the global carbon project. And GIMS is a product derived by Catherine Prigent in France, French teams, based also on satellite with possibly a more careful intercalibration between a series of instruments. The two products have fairly large differences in terms of million kilometers squares on average between WAD2M and GIMS. And the third product that we considered, it's not really a product, it's a model that was already implemented in IFS just for the water cycle. Mainly for the water budget. It's Camaflood model, it's similar to the top model for those who know a bit more of this. And it's only here simulating what I will compare just afterwards, the inundated area, not the permanent wetland area. So which means there is a large differences between the coverage. So the differences are mainly due to the fact that, for example, WAD2M considers subgrid scale compared to the satellite observation, little pond or wetland area, while it does not consider rice paddies, and the Camaflood only considers the inundated areas. So I browsed briefly through different types of analysis, the latitudinal distributions on the left, and we see that although they resemble, the key differences were, one key difference is in the northern high latitude, around 60 degrees north, WAD2M has much more wetland extent. This is debated, there is no ground truth. And on the top of that, it's not because you have a wetland area that it will emit a lot of carbon. If it's a big lake, like the Lake Baikal in the central part, it doesn't have carbon to emit. So we are playing with these, continuing to investigate these differences. And here on the left, this is the difference between the two satellite products, where we see really where in the north, where we have large differences, where the WAD2M has much higher wetland extent. So this will play a role in terms of simulations of the wetland CH4 fluxes. I don't want to go too much into the detail. We also compare the temporal variation, the mean seasonal cycle on the left, and the year-to-year variation. We had only 1 point for the Kama flood. And there is large differences, and we need to select one of these products for the implementation in IFS, especially in the north, the amplitude of the seasonal cycle and the length of the maximum seasonal wetland extent is different between the two satellite products. So what we will do is we are still continuing to improve this comparison, maybe make a more apple-and-apple comparison, working on a new product with GIMS to drop lakes to compare a bit more with the other products, and to compare more with Camaflood. And our target, our ideal target would be still to use Camaflood because it's near real time within IFS, which is a great advantage, but calibrate it, if we can, to match a bit the satellite mean climatology of the data. And in the long term, we investigate also a potential near real-time GIMS product, given that the satellite data are nearly available in near real time. But there is a problem of calibrations that needs to be done. Of course, we won't work only on that. We will also improve this simple statistical model. We will define new wetland functional types based on the global lake and wetland database. And we will optimize the statistical model. We have a strategy for that. We optimize in 2 steps. The first step is to use the FluxNet CH4 data that were recently released and to optimize the temperature sensitivity. I show you here one example that we did in CAMS 41, where we had 2 sites, the observations and the prior and posterior model, CTSL. And we can see that in some cases we can optimize very well the fluxes on the left and not so well on the right in another site in Russia. So really, this is our strategy to calibrate the temperature sensitivity with FluxNet data. And if I come back, then at the end, we will do a global optimization of the wetland emissions, methane emission, using some standard product, either some inversions or some process-based model from the GC, the global CH4 budget. And then finally, our last part will be to improve the statistical model to include some lag effects with methanogenesis available carbon pools, or in some regions, the needs to accumulate a lot of methane before it can escape to the atmosphere. So these delays are important for IFS. I move to the second part, which is improving the CO2 flux modeling, improving the GPP, the gross primary production. In previous phase, it has already been mentioned, we have implemented the Farquhar photosynthesis model compared to the old model. And this was an important step to use fluorescence data because it's much more easy to include a fluorescence model with the Farquhar model than it was previously with the previous model that CTSL was using. So we have calibrated that model, the first Farquhar model at site level. You can see here the improvement at site level where we have a lot of data, the FluxNet data, more than one. We calibrated around 10 parameters per plant functional types. So we made a great improvement. And Anna just gave me the recent evaluation in offline mode of this new Farquhar model against 130 sites, really within in the IFS context. And you see that there is a reduction of the root mean square error with the new Farquhar model. And it was a test also with the leaf area index, where there was an old leaf area index climatology with a new leaf area index climatology. So all is linked, and you have to work on the different aspects at the same time. So, but we were happy that at least CAMS 41 served the purpose of something. It was used in IFS. So at least it was useful. So now what we are doing, we are implementing a fluorescence model. So fluorescence is complicated. It occurs at the leaf levels. during the within the photosystems 1 and 2 that works with the plants. And basically, a fraction of the absorbed light is not used to do photosynthesis, is fluorescent-backed, but also a fraction is used as dissipating energy, the non-photosynthetic quenching effect. And the ratio between these are difficult. It depends on the status of the plant. So we have a leaf level implementation following the scope model, which is a mostly known model. And then you have to deal with all the canopy transfer scheme, how much light escape. If you have fluorescence that is produced at the bottom of the canopy, does it escape and is it seen by the satellite? So we have implemented something. We made a first comparison using tropomy fluorescence data, SIF data. It's not the same scale. So we use site level where we have GPP. So there's a mismatch between the site level where you have GPP and the tropomy, which has a few kilometers grid cell size. But here we compare in CTSL the tropomy data, troposif data. It's not just to have a rough order. Does the CTSL simulation of fluorescence compares relatively with the tropomy data? We only had 2 years for tropomy. It's not the corresponding year here because tropomy is for 2019 and 2020. So we're happy that it first worked. And then what we designed, and it's ongoing, an optimization of this fluorescence model, the key parameters of this fluorescence model, to optimize the mean seasonal cycle at a few set of sites. You can you can get all this data. I think I mentioned here a website where you can see and look at all these results per plant functional types. And we optimize on the other 9 parameters, or 8 parameters per PFT. And in blue, the prior, in orange, the posterior. And we see that we don't fit quite well the tropomy data, but we should not fit them perfectly because there is a size, footprint issues, but we are working on that. It's just first preliminary results. So after we will do a joint optimization of fluorescence using fluorescence data and GPP data that is measured on site in order to ensure that we simulate well fluorescence, but also well the GPP at the same time, not to degrade one with respect to the others. And then in the next phase, we will improve the SIF model, include an explicit radiative transfer model with sun and shaded leaves, and use a 2D radiative transfer model for the escape of the light within the canopy. And we will test different aggregation, midday, raw data versus daily average in order to, at the end, potentially improve the GPP simulated by CTSL. So with that, I want to thank you, and I want just to say it's just one step. You need to continue also to work on CTSL. This is my suggestions for Anna. Well, for the wetland, increase the complexity of the wetland model compared to a simple statistical model, include permafrost fluxes, thermokarst lakes. They may have a short-term impact. And for CO2, I think you should work on respiration a lot, and then possibly include the impact of fire, land management to improve the simulated. Thank you.
Thank you. Thank you, Philippe. Is there any question? Yes, Leonor.
Thank you. It's just a question for information. Thank you very much for this very interesting project that you are having. The question I have is about the leaf area index. You mentioned an old one and a new one, and I want to know what you are using and if you are using any of the data simulated data sets that are there.
I think Anna will reply a bit better than me from the old one and the new one, so HDL.
So when we say old, we mean the current one. The operational climatology of leaf area index is based on MODIS. It's an old climatology. I can't remember exact period, but it's old. But the problem is not, and the new one uses a CGLS product, which is a merge of different, I think, satellite data. And it's available also from CEA. The problem is that is not in the satellite data used or the period used, is the fact that we have to disaggregate leaf area index into high vegetation and low vegetation. And for the MODIS, for the implementation of the MODIS monthly mean LAI, it was decided that we would, that the disaggregation would not be conservative because we wanted to not to shock the system. And in the past, LAI was used per PFT with a constant value. So we tried to minimize the change of LAI. And by doing that, then I think the LAI was overestimated. So what we found is that with the current LAI, with this old disaggregation method, it is not conservative, LAI is overestimated in the winter and in the spring, and that gives an overestimation of GPP, both in spring and in autumn. So we improve a lot as well the seasonal cycle.
It's not a question, but I would like to know, do you know if there are some fluorescence measurement at some sites? Because you are using the tropomi data to make your validation, but...
Yes. There are some fluorescence measurements at some site. Unfortunately, not at all FluxNet sites. We have the Itiala site in Finland, which is well equipped, and where there is fluorescence measurements. And but there are just only a few set of sites. So this is why we choose to use tropomi to have a more extensive evaluation calibration, and it's mostly for the calibration. We would like to calibrate globally. We don't have, like FluxNet, a coverage of all ecosystems in the world with fluorescence data. Yeah.
Thank you. Any other question? No?